Okay, so we looked before at rational expressions that had distinct linear factors in their denominator. Now we're going to look at the case where the rational expression has repeated linear factors. So like before, we first check to make sure it's a proper fraction and the degree of the top is indeed smaller than the degree of the bottom. So we move on now to factoring the denominator of the rational expression. So to factor the denominator of this particular rational expression, the first thing I would probably try to do is to try to factor it by grouping, but because there are four terms, but it turns out in this case that grouping won't work. So the only thing we have to resort to are the factor theorem and the remainder theorem from college algebra. So what that says is if I can find something to use synthetic division on, some x minus k, where k is what I'm using to do the synthetic division, if I get 0 for the remainder, then that x minus k is a factor. That's what I'm going to use to factor this. And the possibilities that I'm going to use for the value of k, the value of the 0 that I'm trying to find, are going to be the factors of the constant, which in this case the constant is 1, over the factors of the leading coefficient. And in this case, the leading coefficient of the denominator here is also 1. So that makes it easy. I'm looking for either positive or negative 1 to be my zeros. If the constant had more factors or the leading coefficient had more factors, I would have a longer list of possible rational zeros. But in this case, since it's a 1 and a 1, I know that the only possible rational zeros are positive or negative 1. So first, I'm going to try positive 1. There's actually a trick for trying positive 1. If positive 1, if you add up all the coefficients and you get 0 as the result, 1 plus 2 is 3, minus 2 is 1, minus 1 is 0, like that, then 1 will definitely work upon synthetic division. So I'm going to use synthetic division here. Let's see, this is going to be 1, a 2. There's no x squared term, so I'm going to put 0 for the coefficient of x squared, negative 2, and negative 1. So the 0 that I am trying is the number 1. If I get a remainder of 0, then x minus 1 is one of the factors of this polynomial, and I'll also get the quotient. So where did I get these numbers from? Those are just the coefficients. 1, 2, there's no x squared, so I put 0, then negative 2 for the linear x, and negative 1 is the constant. All right, so now let's see. Let's do our synthetic division. I'm going to bring this down. 1, and then I multiply 1 by 1 and get 1. I'll add these to get 3. 1 times 3 is 3. I'll add these to get 3 again. 1 times 3 once again is 3. I'll add these to get positive 1. 1 times positive 1 is 1. And you add these and you get 0. So it turns out that the remainder is 0. So the number 1 is a 0 of the denominator there, which means actually that x minus 1 is a factor of the polynomial. Well, since x minus 1 is a factor, x minus the 1 here, then what would be the other factor? Well, the other factor, since this was a fourth degree polynomial, and I took out a factor that was linear, first degree, the quotient is actually going to be a third degree polynomial, and these are going to be the coefficients of that third degree polynomial. So I'm going to have 1x to the third power plus 3x to the second power. There's the 3. And then plus another 3x to the first power, this 3 right here. And then plus 1, this one right here. So here I have the factorization of x to the fourth plus 2x cubed minus 2x minus 1 as x minus 1 times this cubic polynomial. What I need to do is I need to continue factoring um, to make sure that this cubic polynomial is prime. It's actually not prime, it's cubic. So I should be able to get at least one more factor um, with rational coefficients. So let's continue. Well, the next thing you would actually try to do is you'd try to see if 1 were a repeated factor. So you would use 1 on you'd use 1 on the quotient here with synthetic division to see if you can get a remainder of 0. But remember I said that trick earlier that if you add up the coefficients of a polynomial and you get 0 as the sum of the coefficients, then 1 is a 0 of the polynomial. Well, it also works the other way. If you add up the coefficients and you don't get 0 as the sum, then 1 is not a 0 of the polynomial. So that means 1 plus 3 giving me 4, plus 3 is 7, plus 1 is 8. When I add up the coefficients of this polynomial, I don't get 0. Therefore, 1 is not a 0 of this polynomial. So I can't get any more factors of x minus 1. So what I have to do now is I have to try to find some other 0 or some other factor. But once again, I'm going to look at the factors of the constant and the factors of the leading coefficient of this cubic polynomial. And I'm either going to be looking at positive or negative 1. Since positive 1 didn't work by that trick, negative 1 has to be the one that works. So let's see if negative 1 is a factor. All right, so, or is a 0. If negative 1 becomes a 0, that would mean that x minus negative 1 is a factor of the polynomial, x minus negative 1 being x plus 1. So now I'm going to use the coefficients of this cubic polynomial with the synthetic division, which are 1, 3, 3, and 1. So I bring this down. Negative 1 times positive 1 is negative 1. 3 plus negative 1 is 2. 1 times 2, or negative 1 times positive 2 is negative 2. 3 plus negative 2 is 1. And then negative 1 times positive 1 is negative 1. And when I add these, I get 0. So indeed, negative 1 is a 0 of my polynomial, meaning that x minus negative 1 is a factor. So I have this first factor here from before, remember? I have the x minus 1 factor that I've already extracted. And now I've also extracted a second factor of x minus negative 1. So this second factor comes out when I do that second synthetic division of x minus negative 1 or x plus 1. Well, I still have a quotient left over here, and these are the coefficients of my quotient. Since I factored out a linear polynomial, namely x plus 1, out of that cubic polynomial, this quotient here should be quadratic, second degree. And these are the coefficients of my quadratic polynomial. It's going to be 1x squared plus 2x plus 1. All right, so there we have it. That means I've already taken out two linear factors, an x minus 1 and an x plus 1, and I still have this quadratic factor. Well, I could continue along the path I was going along. I mean, I could look for more factors by using the remainder theorem and the factor theorem like I was just doing. But since it's a quadratic polynomial, it should be relatively easy to factor. I mean, it's x squared plus 2x plus 1. And also, it may be possible that this is not factorable over the rationals because it might be irreducible over the rational numbers. But it turns out that we can find two factors. That is indeed a perfect square trinomial. And the two factors of that perfect square trinomial are both x plus 1. So this trinomial here, this quadratic trinomial, factors into x times x to give me the x squared, and 1 times 1 to give me the 1, with plus signs in the middle, and that's the factorization of that. Okay, so I have for this fourth degree polynomial denominator, remember I started off with this rational expression that I was trying to find partial fractions for, and I had a fourth degree polynomial in the denominator, and I got these four factors out of my fourth degree polynomial. So let's drag this guy down here. All that was just a factor. We're just trying to factor. We still have to find the partial fractions here. So let's bring this guy down. And we now know that this rational expression is actually equal to, can be rewritten this way, 3x cubed plus 7x squared plus 4x minus 2, all divided by x minus 1, which is this first factor here. And then we have these three factors of x plus 1. So we have x plus 1 to the third power. We have three factors. So we do have this one distinct linear factor, x minus 1, but we have x plus 1 as a repeated linear factor. It's linear because it's a first degree factor. It's not quadratic. And it's repeated because it's a factor 3 times. So we have one distinct and three repeated linear factors. All right, so what we're going to do is we're going to write the partial fractions. Here's how this works. Each of the denominators of the partial fraction decomposition, each of the denominators has to be either the distinct factor or a power of the repeated factor. So we're going to start off with the first partial fraction. The top has to be a constant, and the bottom would have to be that distinct factor x minus 1, so that it'll be a proper fraction. Then we have plus. Now we're going to start with the repeated. Now we're going to start with the repeated factor. So you have b on top as a constant, and then in the denominator we're going to look at x plus 1 to the first power. Then we're going to have c, a second or a third constant, over x plus 1 raised to the second power. And we're going to go all the way up to whatever the power of that factor is. Basically, you have as many partial fractions as you have factors in your denominator. So then we have d over here, and that's going to be divided by x plus 1 to the third power. So we have these four partial fractions. We have actually four partial fractions here. And each one of them has a constant in the numerator. We have to solve for that constant, all right? So the equation we have is this original is equal to this thing now. Okay, so just like before, we're going to clear the fractions by multiplying by the LCD. If you multiply the left-hand side by the LCD, all the factors will cancel. The factor of x minus 1 and the three factors of x plus 1, leaving only the polynomial in the numerator there, which is 3x to the third, 3x to the third, plus 7x squared plus 4x minus 2. And this is equal to now, well, let's clear the fractions on the right-hand side. When I multiply this by the LCD, remember the LCD is x minus 1 times x plus 1 to the third power. So when I multiply this first partial fraction by the LCD, what's going to happen is the factor of x minus 1 is going to cancel, that factor right there, and I'm going to have the three factors of x plus 1 left over to multiply by a. So that's going to result in a multiplied by x plus 1 to the third power. 1 to the third power. Okay, then I move on to the next term. When I multiply this term by the LCD x minus 1 times x plus 1 to the third, one of the factors of x plus 1 cancels, leaving me an x minus 1 factor and two factors of x plus 1. So it's going to be x plus 1 squared. So the next thing is plus b, and I still have the factor of x minus 1. That didn't cancel. But one of the factors of x plus 1 cancels, leaving me x plus 1 to the second power. And then c now, the term that has c for the numerator. This term right here. Well, in this case, two of the x plus 1 factors will cancel. Two of them will cancel. And I'm going to be left with a single factor of x plus 1 with the factor of x minus 1. So I still have the x minus 1 factor, x minus 1. But now I only have one factor of x plus 1. And lastly, the term with d for the numerator. With this term now, all three x plus 1 factors cancel, and you'll be left with only the factor of x minus 1. So d is then only multiplied by x minus 1. So x minus 1 is the only factor left here. All right, so when you clear the fractions, you get this resulting equation. All right, so what we're going to be charged with is finding A, B, C, and D, which are the numerators of our four partial fractions, respectively. All right, so what we're going to do here is we're going to use the trick that we used last time. We're going to look at each of the factors of the original denominator and ask ourselves what the zero of that factor is. So one of our factors was x plus 1. That factor, x plus 1, has a 0, negative 1. So I'm going to let x equal negative 1. That's what I'm going to do. I'm going to let x equal negative 1 first. That's my first step, okay? So when I let x equal negative 1, on the left-hand side, I'm going to have 3 times negative 1 cubed plus 7 times negative 1 squared plus 4 times negative 1 minus 2. On the right-hand side, well, let me see. When I plug negative 1 into this term right here, it's going to make this factor into 0. It's going to be negative 1 plus 1, making this a 0 times a. So I'm not going to write that. That's just going to be a 0. When I plug negative 1 into this term right here, that also becomes a 0. 0 squared is 0, and 0 times b times x minus 1 would also be 0. So this term will be 0. As a matter of fact, any term that contains the factor x plus 1 will turn into a 0. So this term here will also be 0. Negative 1 plus 1 would be 0. 0 times this would be 0. And I'd only have this term left over, which is d times negative 1 minus 1. So what I've done is I've plugged negative 1 everywhere in this equation. A bunch of these terms dropped out because they had a factor x plus 1, and negative 1 makes that 0. The only one left was this, and this is the new equation I get by letting x equal negative 1. Let's see what I get over here. So this would be negative 3. Negative 1 to the third power is negative 1 times 3 is negative 3. This would be positive 7 because negative 1 squared is positive, plus 7. This would be a negative 4 minus 4. And then we have here minus 2. Minus 2. And this is equal to negative 1 minus 1 is negative 2d. So this is negative 3 plus 7 is 4. 4 minus 4 is 0. And 0 minus 2 is negative 2 equals negative 2d, which tells me that d is equal to the number 1. D is the number 1. So I found d by letting x equal -1, which was actually the 0 for this factor. The other factor, this one right here, this factor right here, the 0 of that factor is +1. If I plug +1 in there, it will make that 0. So now I'm going to let x equal +1. When I let x equal +1, let's see what I get. Well, I'm going to replace everything that I had there with a +1. As a matter of fact, let me bring it down so to where I can see it. All right, let's bring this down a little bit. And let's bring this thing down, because what I'm going to do now is I'm going to replace all the x's in this expression here with +1. So let's bring that down here so I can see. So once again, I'm going to take this and I'm going to replace all the x's with +1. So I'm going to have 3 times +1 to the third power. So that's going to be 3 times 1 to the third power plus 7 times 1 squared plus 4 times 1 minus 2 is equal to, and let's see, this is going to be a times 1 plus 1 to the third power. Now this factor here is going to become 0. So I have 1 minus 1 is 0. So this entire term would be 0 if I plugged in 1 for x. As a matter of fact, any term containing the factor x minus 1, like this term right here and this term right here, will all turn to 0. Therefore, this will be the only term left. And what I'll get here is 3 plus 7 plus 4 minus 2 is equal to 2 to the third power times a, where 2 to the third power is 8. And on the left hand side, I have 3 plus 7 is 10. 10 plus 4 is 14. Oops. Let's see. And 14 minus 2, I think I copied that incorrectly. Yes, the original problem is a minus. All right, so no, I didn't copy correctly. And I get 13, let's see, 7 plus 3 is 10 plus 4 is 14, and then 14 minus 2 is 12. So I get here a 12. And then in order to find a, I divide both sides by 8. And I get a then is equal to, looks like 3 halves. All right, so I found now a value for a and b in this partial fraction, or sorry, a and d in this partial fraction decomposition. I now need to find b and c. All right, so let's go ahead and do that. So I don't have any other zeros, because remember, there are only 2 factors that were actually distinct, x plus 1 and x minus 1. The other factors were also factors of x plus 1. So I have no other zeros to plug in. So what I have to do here is I have to plug in everything I know and just equate coefficients on each side. Let me show you what I mean by that. So I still have this thing here. And I'm going to copy it, putting in all the things that I already know. For instance, 3x to the third plus 7x squared plus 4x minus 2. I know a is 3 halves. I know that for a fact because I've just found that. And I'll have x plus 1 to the third power plus, I don't know b, x plus 1 squared. I don't know c times x minus 1 times x plus 1. What I do know is that d is equal to positive 1. So I know that d is just positive 1. So all I have here, my last two terms are plus 1 times x minus 1. So I plug in everything I know. And then what I'm going to do from here is I am going to clear out the fractions by multiplying everything by the denominator here, 2. So I'm clearing the fractions to get 6x to the third power plus 14x squared plus 8x minus 4 is equal to, the 2 would cancel here, leaving me just 3 times x plus 1 to the third power, and then plus 2b times x minus 1 times x plus 1 squared plus 2c times x minus 1 times x plus 1, and then plus 2x minus 2. So I multiplied every term by 2 to clear the fraction. And then what I'm going to do is I'm going to make sure that the coefficients on the left side match up with the coefficients on the right side. So basically, the coefficient of x cubed on the left side should match up with the coefficient of x cubed on the right side. The coefficient of x squared on the left should match up with the coefficient of x squared on the right. Coefficient of x on the left should match up with the coefficient of x on the right. And negative 4 should be the constant on both sides. So in order to do that, I have to multiply the entire right-hand side out. So let's multiply the right-hand side. All right, so I still have all of this here on the left. So let's take this and copy it. And actually, we don't need all of that. Let's erase some of that. And then on the right-hand side, we're just going to multiply it all out. So, okay. Let's see the multiplication. When you multiply this, you can use the binomial theorem to do this, or Pascal's triangle. But when you multiply, this is going to turn into x to the third plus 3x squared plus 3x plus 1. All right? And then when you multiply the second thing here, the x minus 1 times x plus 1 squared, well, let's keep the 2b in front, plus 2b. But when you multiply all that out, let's see. What we get is we get x cubed plus x squared minus x minus 1. That's when you multiply out x minus 1 times x plus 1 squared. All right, obviously when you multiply x plus 1 and x minus 1, that's a difference of squares. So you get 2c times x squared minus 1. And of course, we still have our plus 2x minus 2. Now I'm ready to distribute everything on the right-hand side. So on the right-hand side, I'll have 3x cubed plus 9x squared plus 9x plus 3. And over here, I'll have 2bx cubed, 2bx cubed plus 2bx squared, 2bx squared minus 2bx and minus 2b. And I will also have from this, when I distribute, a plus 2cx squared and a minus 2c. And then, of course, I still have the plus 2x and the minus 2. Okay, now what I'm trying to do is I'm trying to equate the coefficients of each of the powers of x. So I have to group them first. So let's match them up, all right? Here I have the x cubes. This is x cubed. This is x cubed. So I'm going to group those two together to get a 3 plus 2b x cubed. X cubed. All right, let's take a look at the x squareds now. Here's an x squared, and here's an x squared, and here's an x squared. So for x squared, I have plus, and then I have a 9x squared, and I have a 2b x squared, and I also have a 2c x squared. So those are the terms that involve x squared. And then let's see, the x's. Here I have an x, uh, here I have an x, and here I have an x. So I have plus, and then for the x I have 9 as one of my coefficients, a minus 2b as one of my coefficients, and a plus 2 as one of my coefficients of x. And then it's just a matter of looking at the constants. So let's see, everything left is a constant. So here's a constant, here's a constant, here's a constant, and here's a constant. I have 4 constants, which are 3 and minus 2b and um, minus 2c and a minus 2. All right, so that means that the coefficient on the left of x cubed, which is 6, has to be equal to 3 plus 2b. So 6 has to equal 3 plus 2b. The coefficient of x on the left, which is 14, or x squared, I mean, the coefficient of x squared on the left has to be 9 plus 2b plus 2c. The coefficient of x to the first on the left, which is 8, has to equal 9 minus 2b plus 2. And the coefficient, the constant on the left, which is negative 4, has to equal 3 minus 2b plus minus 2c minus 2. All right, so we can find what we need from here. For instance, I can find b because I know that 3 plus 2b, the coefficient of x cubed on the right-hand side, has to equal 6. The coefficient of x cubed on the left-hand side, which tells me that b is equal to subtracting 3 halves. So b is 3 halves. All right, that's great. I have b now. The only thing I need now is c. Well, here's a relationship. I know that 9 plus 2b, which I just found out to be 3 halves, plus 2c, which is the coefficient of x squared on the right side, has to equal 14, which is the coefficient of x squared on the left side. So let's see what we get here. The 2's cancel here, leaving me 9 plus 3, which is 12, plus 2c is equal to 14. And then I subtract 12 from both sides, so 2c is equal to 2, which means c is equal to 1. So there I have all of my constants that I needed. Let's gather them here. I have a here, right? So I had a, And I also had b. I think b was equal to 1, right? Oh, no, not b. We had d. So we have a equals 3 halves, b equals 3 halves, and we had d in the very beginning equaling 1. So d is equal to 1. So there we have everything we need. We found all the numerators. So now it's time. We have d equals 1. Now it's time to plug them all in to our partial fraction decomposition that was proposed in the beginning, and we will have the final answer here. So let's see. All right, so we have our values for A, B, C, and D. So this is the partial fraction decomposition of the original rational expression. A, which is 3 halves over x minus 1, plus B, which is also 3 halves, times x plus 1, plus C, which is 1 over x plus 1 squared, plus D, which is 1 over x plus 1 to the third power. You simplify this a little bit because you have improper fractions there. You're going to take the numerator, keep it the same, flip the denominator so it becomes 1 over x minus 1, and then multiply. So you're going to get here 3 over 2 times x minus 1 plus 3 over 2 times x plus 1 done the same way, plus 1 over x plus 1 squared, plus 1 over x plus 1 to the third power. And there you have it. That's the partial fraction decomposition when there are repeated linear factors.